Okay, thank you. Every year, except last year because of an unfortunate storm, the Royal Irish Academy celebrates Hamilton Day to commemorate William Rowan Hamilton's groundbreaking discovery in 1843. The day includes an award ceremony to recognise the most gifted third-level mathematics students in Ireland, and I believe some of them are with us this evening, a masterclass for early career researchers, and the Hamilton Lecture itself, which is given by an internationally renowned speaker. Our speaker today is Professor Martin Hairer, originally from Austria and son of a mathematician, I believe. Martin received his BSc, Masters and PhD from the University of Geneva. He's currently Professor of Pure Mathematics in the Department of Mathematics at Imperial College, London. He's advanced the field of stochastic partial differential equations by providing a toolkit which addresses problems that were previously thought to be inaccessible. His work is also furthering more general areas of stochastic dynamics and stochastic analysis, part of mathematics concerned with random processes. His breakthrough approach to the nonlinear Kardar-Parisi-Yang equation allowed him to mathematically resolve the meaning of this equation and its solutions. Subsequently, he used his ideas to create the theory of regularity structures, which provides a way to tackle a broader class of stochastic PDEs. In August 2014, Martin was awarded the most prestigious prize in mathematics, the Fields Medal, which he received for his outstanding contributions to the theory of stochastic partial differential equations, and in particular for the creation of a theory of regularity structures of such equations. He's received a number of other prestigious prizes and awards. He's a Fellow of the Royal Society and the American Mathematical Society. He's also a member of the Austrian Academy of Sciences and the German National Academy of Sciences, Leopoldina. In his lecture tonight, entitled On Coin Tosses, Atoms and Forest Fires, we will encounter some of the mathematical objects that arise naturally in probability theory, as well as some of their surprising properties. In particular, we'll see how one of these objects was involved in the confirmation of the existence of atoms over 100 years ago, and how new properties of related objects are still being discovered today. So without further ado, I ask Professor Hairer to deliver the 2018 Hamilton Lecture.
Thank you very much. Thank you very much for this kind introduction. And well, I'd like to thank the Royal Academy for organizing this event and for having me here in Ireland, my first trip to Ireland. And so maybe I should start by, since not everybody, obviously not everybody in the audience is a mathematician, and maybe not everybody in the audience even sometimes knows what mathematicians do all day. So let me just try to give you a quick idea. I mean, anyway, sometimes one gets the impression that mathematics is somehow about numbers. And of course, in a way, it's similar, it is about numbers, but in a way similar to the fact that writing a novel is about letters. So yeah, I mean, I suppose they make some theorems, but that's about it. In some sense, mathematics is really more about sort of exploring the world of ideas. Right? So it's sort of like in Plato's story about the cat. So we are sort of sitting down there in the real world, but there's actually the idealized sort of world of ideas out there, and we just see a glimpse of it. And to some extent, mathematics is about trying to explore that world of ideas. Right? And so numbers are just one of the simplest abstractions, the ones that are part of this world of ideas and that have some reflection into your life. But we're generally interested in all types of abstractions. And so personally, the area of mathematics that I work on is probability theory. And so then again, so sometimes when you say you work in probability theory, so people will tell you, oh, so you make a lot of money in the stock market, or do you bet on horse races or something like that? And so no, I don't. don't matter those numbers, don't back on horse races. And being a probabilist might help me in the horse races, but maybe not all that much, not enough to make a significant income. So what probabilists are mostly interested in is you have various rules of transforming probabilities. So you know some of these rules, so you know that if two events are independent, then the probability that they both occur is the product of the probabilities. So you know about these sort of simple rules for manipulating probabilities. But then you have these rules for manipulating them, they still have to come from somewhere in the first place. And so in probability theory, there are essentially two kind of guiding principles that allow you to come up with probability. And so the first one is one that you're probably all familiar with to some extent, which is symmetry. So what symmetry says, so symmetry shows up in many parts of mathematics. And in probability theory, what symmetry tells you is that imagine that you have some experiment of which, well, you cannot predict deterministically the outcome of the experiment. And there are, a number of possible outcomes. And as far as you're concerned, you're able to distinguish between these different outcomes. But as far as the mechanism of the experiment is concerned, that mechanism that produces the outcomes doesn't distinguish between them at all. And if that's the case, then, well, you'd expect each of these outcomes to occur with the same probability, because the mechanism that produces them cannot distinguish between them, and so it doesn't have any reason to favor one over the other one. Right? And of course, the easiest example is the coin toss. Right? So if you toss a coin, the mechanism of the coin spinning in the air doesn't care about which side is heads, which side is tails. But then, of course, once you look at the coin, you can easily see which one is which. Right? So that's a typical example of symmetry. So you have two possible outcomes. They are completely equivalent as far as the mechanism that produces them is concerned, and so you would give the same probability to each of them. So, now, there's a second mechanism that shows up in probability theory, which is much less known outside of mathematics, outside of physics. And so that's a concept which is known as universality. And so that's really a concept that actually comes from physics. So it shows up a lot in theoretical physics, but it's also reflected in probability theory. And what universality tells you is that in many cases, when you have, if you want, relatively complicated random systems with many different independent parts that kind of act together in order to produce some kind of large, if you want, random outcome, then very often what happens is that that large random outcome doesn't really care too much about the precise description of what happens at the small level. And so the standard, the classical example, which you would learn in your undergraduate studies, at least if you study mathematics, I don't know if one still teaches it at high school, is the central limit theorem. And so what the central limit theorem tells you is that if you add random quantities that are more or less independent and that are all relatively small, and so you add them all up, you get a large random quantity, then the distribution of that large random quantity is always more or less the same. And so it's always distributed according to this bell-shaped curve. So what I mean by this is, well, so for example, one thing that you can do is toss coins, and then you count how many heads you get, right? So it basically means that you add up random quantities because you add 1 whenever you get heads and 0 whenever you get tails. So you just count the number of heads. And then you do that many times and you look at how many heads you get, right? So say you do it 50 times, you count how many heads you get, and then you repeat the experiment. And you do a statistics, and you get something like this. So this is if you do 1,000 runs of this experiment, and then you plot sort of how often you get So 50 is somewhere in the middle, right? So most of the time you get about 50 hands, roughly. But then occasionally you get 48 or 52 or 49. And so here there's a little plot of the frequencies of the different outcomes. So 50 somewhere in the middle, and then 51 here, 52, 53. And it all roughly follows that bell-shaped curve. And so if you make more and more runs of such an experiment, then it gets closer and closer to this bell-shaped curve. It's called the Gaussian distribution. And it's always the same, so that's why whenever you see statistics or probabilities, this kind of bell-shaped curve shows up very often, and it's for that reason, right? So it doesn't matter that you add up coin tosses. You could add up other types of random quantities. They don't even have to be completely independent. You always end up with that bell-shaped curve. Now, so let me try to sort of expand a little bit about these two ideas. And so even the first one, so the simple idea of symmetry, sometimes you have to be a bit careful about it, right? So let me take an example, which is called the two envelopes problem. And so it's the following situation. So imagine that I have two envelopes, and the only information I give you, both of them have some amount of money in them. And the only information I give you is that one of them has twice as much money as the other one. Okay, but you can't see inside. And then I ask you to choose one of the two envelopes, and you open it, and you see that, say, there's 10 euro inside. Okay? And now I give you a choice. So either you keep the 10 euro, or you get what's in the other envelope. Okay, but if you open the other one, obviously you're not allowed to go back if it's a smaller amount. And so then the question is, what should you do? Right? So should you keep the 10 euro, or should you actually take what's in the other envelope? And so if you apply that symmetry argument, well, what would it tell you? Right? So there's two possibilities. Since the only information I gave you is that one of them has twice as much money as the other one, means there's, in the other envelope there's either 5 euro or 20 euro. There's no other possibility. And then, the two situations are probably symmetric. I didn't give you any other information. And so then, should you switch or not? Well, if you switch, then how much would you get? So there's a half chance that you get 20 euro, and there's a half chance that you get 5 euro. So on average, you get 12 euro 50, which is more than 10, so you should always switch. But of course, you didn't even need to look at what was in the first envelope to know that, right? So you could just have switched in the first place. But then, since it didn't make any difference, well, it's obviously a nonsensical answer, right? So what actually went wrong here in the reasoning? So there's various things that went wrong in the reasoning, but the main thing is that actually, obviously, it is not quite simple, right? So one always has to be a bit careful when you apply, you try to apply mathematics to the real world, so you try to come up with some sort of cute, clean mathematical model that models some aspect of the real world. And then you somehow believe that the answer that the model gives you tells you something about the real world. And, maybe you can prove a theorem about the mathematical model, but that's not a theorem about the real world. It's a theorem about the mathematical model. And that theorem doesn't tell you whether the model actually describes the world or not. So one always has to be careful when, relating mathematics back to the real world. In this particular case, I sort of sometimes tricked you into believing that the two choices here are equivalent. I mean, obviously in reality they're not, because, suppose that I take an extreme example, right? So you open the envelope, it says 100,000 euro. Now, do you really think I would give you 200,000 euro? Right? So obviously the other one would have 50,000. Right? So the different possibilities are not equally likely, and actually there is no probabilistic model in which all possibilities would be equally likely. Because you kind of have a probability distribution where all possibilities are equally likely, right? So what we did here is we got a nonsensical conclusion because we kind of tricked ourselves into doing calculation on a nonsensical model. For the math student in the audience, we can actually come up with a model, with a proper mathematical model, where you still get the conclusion that you should always switch. And then maybe the exercise for, if you're bored between now and the end of the lecture, is to try to figure out what was wrong there. That's one thing. I mean, so if you want the serious point here that I want to make is that one has to be kind of careful when one tries to sort of, bully people into believing something, or into accepting a point just because there is some mathematical statement that tells you something, right? Because you always have to go back and see, it's a mathematical statement about the mathematical model. Does that model actually reflect the real world? And there can be really dramatic consequences when you get these things wrong, right? So there's this famous case of Sally Clark, which many of you probably heard about. So what happened with Sally Clark, she had an infant child that died of cot death, sudden infant death syndrome. And then a couple of years later, she had a second child, and the second child also died of sudden infant death syndrome. And so then someone reported her to the police because they thought it was suspicious, and maybe she had actually murdered her children. And there was no evidence, if you want. So the only evidence was probabilistic. Right? It was just saying this is very unlikely to happen in a family twice in a row. And so she was convicted, she was tried, and during her trial there was an expert witness who came up with statistics and says, well, in a middle-class family with that type of background, in that kind of area, the probability that one child dies of sudden infant death syndrome is about, I don't remember what was the figure, 1 in 20,000 or something like this, and therefore the probability that it happens twice in a row is 1 in 400 million, and therefore she must have murdered the child. And so she got actually sent to prison until a few years later. Then there was an appeal, but it took a very long time, and she got retried. She got acquitted, but then by that time it was too late, and I think 2 years later she basically died of alcoholism or something like that. I mean, her life was completely destroyed. And so of course the mistake, I mean, the expert witness made in a way 2 different mistakes. One was a mathematical mistake, one was a modeling mistake. Right? So the modeling mistake was to assume without any evidence, if you want, that the 2 events were independent. But clearly there might have been a genetic basis or something, and then they wouldn't be independent. And then there's also a mathematical mistake, which is that one chance in 400 million sounds like very, very small, and so you say it would never happen. But there are 30 million families in the UK and so on. So if you try 30 million times, things that happen once in 400 million do actually happen. So that was one has to be extremely careful when one sort of makes these kind of inferences about reality, because it can have consequences. So let me now go back to this, to this other idea of universality. So what I want to do is now I want to show you, so I kind of try to explain a little bit the central limit theorem, which is an example of universality. So now I want to explain, if you want, the second simplest universal object that shows up in probability theory, and that's called Brownian motion. So Brownian motion, well, okay, so it's named after Brown. In a way, it was first described by Egan-Luce, actually, about 30 years earlier, or 40 years earlier. So it's what you see. So it's what you see in this movie. So what you see here, essentially you take little specks of dust or pollen or something like this. So in the case of brown, it was pollen suspended in water. In the case of Higginboos, it was coal dust suspended in alcohol. You look at it under a microscope, and you see that these little particles move around in some erratic way like this. And you try to explain what's going on. Now, so when Brown looked at this, so since he was looking at grains of pollen that came from a plant, he thought that maybe these things were actually somehow alive, and so that they were moving erratically under their own motion. But then he discarded that pretty quickly. And so then the next explanation that people came up with is the one saying that, well, actually what's going on here is that these little particles, they're suspended, say, in water, but then water is actually made up of water molecules, and the water molecules are really kind of like ping pong balls, so they sort of just move around sort of in a straight line, and they bounce off each other, and so then what happens is that they bounce off these little grains of pollen, and every time a molecule of water bounces off the grain of pollen, it gives it a little kick in one direction. Of course, that kick is very, very small, so you wouldn't see the effect, but there are many, many, many molecules of water, so they all sort of kick that grain of pollen in all directions over time, and the cumulative effect of all of these kicks produces a kind of erratic motion. Right? So now, what you'd like to do is to come up with, some kind of mathematics. So you'd want to come up with some kind of mathematical model of this phenomenon. And so the tools to do that, so one of the tools is actually developed by Fourier. So Fourier was a French scientist. This is very well known in mathematics. He's actually also quite well known to historians because he took part in Napoleon's invasion of Egypt, and so he was actually running the museum in Cairo for a year or something like that, so he had a non-trivial part to play there. But mathematically, what people remember him for is essentially two things. So one, which is called Fourier Transform. So the Fourier Transform, what it says is that essentially you can always write, if you have a signal, like for example a sound wave, you can write it as a superposition of pure waves. Right? So you have a sound wave like this, so it's some kind of complicated signal. You can always write it as a superposition of pure waves like that. And that's something which is used quite a lot in, for example, digital compression of sound files, right? So if you have an MP3 file, how does MP3 works? Essentially, it takes a chunk of sound, it decomposes it into these pure waves, and then it uses the fact that in many cases, some of these amplitudes are very small, many of them are either very small, close to zero, so you just store the values of these amplitudes, you cut away the ones that are too small, and then that gives you much less information to store. And that works pretty well, so that's MP3. And the other thing he's well known for in mathematics is Fourier's law. So Fourier's law describes, so I'm not going to ask you to, I'm not going to do an exam at the end of the lecture. You have to remember that equation. It's just to sort of give you sort of impressionistic feel of what the equation looks like. So that's the equation that describes how heat propagates in a solid. Right? So what it tells you is, well, you have a solid which is, say, hot. It's hot here, it's cold here, and then the hot bit is going to kind of spread over to the cold bit. And you want to have some equation that actually describes how heat spreads through your solid. And Fourier came up with the equation that describes this. Now, why am I telling you that? Right? So that doesn't seem to have anything to do with this grounding motion. Well, so in the early 1900s, so 1905, well, 1905 and 1906, well, two people of which you know certainly. The first one, so that's Einstein, when he was young and didn't yet look the way he looks in most of the pictures you've seen. So Einstein and Smoluchowski was an Austrian physicist. So they was independently about the same time. So built a more quantitative theory of Brownian motion, trying to really predict where you would find these grains of pollen after a while, right? So the idea is, well, say you have these grains of pollen that sort of move around in the fluid. So you see your grain of pollen here at a given instant of time. Now you close your eyes, you look at it 10 seconds later, where you're going to see it. Now, of course, it's going to be random, so I can't tell you will see it here, right? So there's no way you can predict the precise location. But you can say, well, it's more likely that you would see it around here than you would see it over there, right? So you can kind of predict the probability distribution of where you're going to see that grain of pollen. And that probability distribution is going to evolve over time, because if you wait for longer, then, well, it's going to be more likely that it moved a bit further away. Right? And if you wait for a very short time, it's not going to move very far. And it turns out that the equation that governs this probability distribution is actually exactly the same as the heat equation that Fourier had written down 100 years earlier. So you should think of, if you want, it's the probability of finding the particle at a given location at a given time, which plays the role of the temperature, if you want, at a given location at a given time in the heat equation. Right? So the two quantities, conceptually, they have nothing to do with each other, but mathematically, the equations that govern them are exactly the same. And so what Einstein and Smoluchowski did is, well, so they made first this prediction that the probability of seeing particles is governed by this heat equation. And this actually comes with quantitative predictions, so you can essentially predict how far, as a function of the weight of the grain of pollen, the things that you already knew about the water at the time, you can kind of predict how far it would move in a given amount of time. And the reason why that was very important is because at the time, although people very strongly suspected that water and all matter was made of atoms and molecules, there hadn't been any experiment that verified it for sure. Right? So all experiments that people did, so it was all consistent, if you want, with this assumption that matter was made of atoms and molecules. But you could always have come up with some other explanations. Right? And so then some people were kind of reluctant to embrace that atomistic description of matter, because they say, well, you can always come up with this ether, you can come up with whatever kind of explanation to actually explain the experiments that people had at the time. And so this was one experiment where the quantitative predictions Einstein and Smoluchowski made could not be explained in any other way than by water being made out of atoms and molecules. And so then, well, Hairer, a couple of years later, he actually did the experiment to check whether the predictions were correct, and they were correct, and so he got the Nobel Prize for that, because this was really the experiment that then settled the debate about the existence of atoms. By the way, if you're curious, actually the thesis of Hairer in which he describes the experiment, if you Google it up, you can actually find it online. It was scanned. You can easily find it online. It's actually very nice to read. It's very well written. It's a very nice thesis to look at. So, by the way, incidentally, the same object was in a way, discovered in a completely different way at around the same time, but actually before Einstein and stochastic, by another French guy called Bachelier. And so Bachelier, what he did in his thesis, so he was interested in figuring out how the stock market works. Okay? And so one little story that he was telling himself is that, well, so how do stock prices change? Well, there are lots of people buying and selling stocks on the stock market, and every time somebody tries to sell a stock, well, it creates some more offer, and so that drives the price a little bit down. Now, of course, if you or me try to sell 2 shares in some company, obviously it's not going to make much difference to the price of that company, right? I mean, so presumably there are not that many billionaires in the room. So for most of the, most actions of most people who buy and sell shares have an essentially negligible impact on the stock price, but there are many, many such people, right? And so altogether, all these actions do actually succeed in moving the stock price. And you see the story is pretty much the same as the story with the pollen and the water molecules, right? With the sort of grain of pollen being the stock price and the water molecules being people trying to buy and sell shares. And so he came up with exactly the same equation. So he already realized in 1900 that you can actually describe the evolution of stock prices by that same heat equation that Fourier came up with 80 years earlier. So just for the little story, so it's kind of interesting because so that work, it really was the starting work for modern mathematical finance, right? So sort of like the model 101 of stock prices that banks use is essentially variants of that model, right? I mean, of course, this model is, if you want, very naive, and it doesn't really, it's a very, very basic model, but it is the starting point, actually, of most models of stock prices. So he essentially invented mathematical finance, but it didn't do him much good because, well, first, the French probabilists at the time hated that. And so they thought, this is not proper mathematics, and it's, sort of not beautiful enough. And, so they didn't like his work at all. So he had a hard time finding a job. So he had a job in Paris, but then the First World War broke out, and so he got drafted, so he lost his job. And then when he came back from the war, well, the job was gone, and he wasn't given any other job, and it took him until he was in his 50s or something like that, until he finally got a permanent job. So he spent most of his life essentially doing tutoring work and temporary jobs. Of course, now, basically his work sort of laid the foundations of Flatten-Scholes, which is sort of the basic model in mathematical finance, which got the economics Nobel Prize in the 90s, but he didn't even get a job out of it. So we have this, so you see this aspect of universality also. So you have two completely different situations. So one of them is the grains of pollen that sort of move around in water. The other one is the stock prices kind of move up and down. Microscopically, the mechanisms are very different. Of course, the story that you tell yourself is roughly the same. Right? So if you want to do a precise mathematical description of what happens at small scales, it would be a very different description for the two situations. But you tell yourself sort of the same story. And now what happens is that since both have kind of the same story, you have this universality which tells you that actually, the quantities that you care about are essentially the same in both sides. And, well, so mathematicians, of course, try to make that precise. And so first, one thing that you would want is, you see, so this heat equation, what it tells you is it gives you some kind of description of the probability of finding say, the particle at a given location, given time. You would like to also have some kind of mathematical object that really describes the trajectories of that. So these kind of erratic trajectories of this particle. And the guy who came up with that mathematical object, that's Norbert Wiener. So he was professor at MIT. He worked in various areas of mathematics, so he did lots of different things. But he came up with the mathematical object that really describes the shape of these trajectories. Coincidentally, so one thing that he was also interested in was noise suppression in sound recordings. And so there's something called the Wiener filter in digital signal processing, and that refers to the same Wiener. And there are, for example, these noise-canceling headphones, where one of the brands is Bose, and the Bose who created the company Bose was actually a PhD student of Wiener. So he came up with this one, the mathematical description of these kind of trajectories. Right? So the kind of object that you're trying to describe is something like this. So this would be now the idealized object. This sort of looks like a stock price, right? So locally stock prices roughly look like this. And so what you see is this object, so it has some kind of self-similarity properties, right? So here what I do is I take one trajectory, so if you want, it would be like one trajectory of something like a stock price or so. And then I just zoom out. And you see, it changes, but it always kind of looks the same. So it has some kind of fractal structure in the sense that you can zoom out as much as you want. It always looks similar. These two parabolas here, what they mean is that the way you have to zoom out is the way which keeps these parabolas the same. So it means that actually when you zoom out by a factor 4 horizontally, you only zoom out by a factor 2 vertically. Right? So the zooming out, the vertical zooming out is sort of the square root of the horizontal zooming out. So Wiener came up with the proper, if you want, mathematical description of such a random fractal object. And then so Donsker, a few years later, he, if you want, formulated one of the first mathematical theorems that underpinned that concept of universality. So now, let me try to, so this was all, if you want, early 20th century mathematics. Right? So there's this Brownian motion. Essentially, by the time we get to the 40s or so, 40s or 50s, it's pretty well understood. Somehow the mathematics is very clear. But there are actually other somewhat similar situations where the mathematics is much less clear, and so essentially hasn't really been understood until very recently, or is still not completely understood. Actually, in most cases, it still isn't really understood. And so one example which was understood relatively recently is that of interface growth models. So what we are looking at here is a situation where you have two regions in two-dimensional space, and you have an interface that separates between the two regions. And one of the regions is somehow more stable than the other one. So the stable region wants to invade the unstable one. Right? So one of the two regions invades the other one, so the interface moves. The motion of the interface is somewhat random. So that's the forest fires that I referred to in the title would be such an example. So you have one region is the part of the forest that's already burned down, one region is the part of the forest that's not yet burned, and obviously it's the burned down part that invades the not yet burned part. Right? And that invasion happens in a somewhat random way because sometimes some bits burn a bit faster than others. And so at some locations the front moves a little bit faster, some locations it moves a little bit slower. Right? So it's that kind of situations that one has in mind. And now what we're interested in as probabilists is to try to understand, if you want, the random fluctuations of this front. And so here is, so for example, this is an experiment. So this is an experiment where people were able to do very precise measurements. So it's a real experiment. But what people did is they took a liquid crystal, like the sort of liquid crystal that you have in display of your TV or your phone, and it comes in two different states that have two different optical properties, so you can kind of see the difference between the two. And one of them is more stable than the other one, and you prepare it in the unstable one. And then you shoot a laser at it, and where the laser hits the liquid crystal, it gives it enough activation energy to flip over into the stable state. And so essentially with the laser you can kind of paint a line of the stable state in that liquid crystal. And then the stable state being stable, it wants to invade the unstable one, right? So you kind of paint that thin line on the liquid crystal with your laser, and it thickens out. And so then you just take pictures every second or every tenth of a second or something, and you look at where the front, where the border of that region is at every given instant of time. And so here is, so that's what you then get, what color is time, if you want, right? And the location of that border. So it moves in time, and you see these random fluctuations. And so you can come up with various sort of mathematical models that have this feature. So they would all be different kind of toy models. So let me show you an example of a model, one of these models. So the kind of models that we're thinking about is like that, right? So this here is basically a Tetris game where you don't play. Right? So the Tetris bricks just pile up by themselves. And so, well, so it is a model like that because you have two regions. There's the one which is filled by Tetris bricks, and there's the one which is not filled by Tetris bricks. And obviously the one which is filled by Tetris bricks invades the one which is not, because we only add bricks and we never remove them. Now, of course, if you look at this here, it really doesn't look like what we saw on the previous slide, right? So it might be a bit of a lousy model for that. But actually, if you look at what happens on kind of larger scales, right? So if you zoom out, you see something like this, right? So it's exactly the same model. Now I just look at what happens, when you have hundreds of thousands of Tetris bricks falling down. And so now you don't see the individual bricks anymore, and what you see actually starts to look pretty close to what we had in that experiment, right? So it's maybe not such a bad model after all. Now, obviously, nature is not made of Tetris bricks, and liquid crystals are not made of Tetris bricks, right? So it's certainly not a good model of what happens at the microscopic level. But the point of this notion of universality is essentially what happens at the microscopic level doesn't really matter as long as you get the story right. And then what you see at large scales should essentially always be the same. Now, in this particular case, there's absolutely no mathematical theorem that tells us anything about the kind of large-scale behavior of the Tetris model. And actually, very few models on which you can, really describe what happens at large scale. So in this particular example, it turns out that there's only one very specific model of interface growth where one can compute all sorts of things explicitly, and so people were able to show that for this very specific model, if you zoom out and you scale things in the right way, then there is a limiting object. And now the object, it's not like the Brownian motion was just a random function of time, so now it's a random function of space-time. Right? So this interface is a function of time, but it's also a function of space. Right? So it's now a curve that moves randomly. It's like a random movie, if you want. So it's a somewhat more complicated kind of mathematical object that people have only started to understand very, very recently. Right, so this is called the KPZ universal. So KPZ refers to Kadar, Parisi, and Jang. So there were three physicists who sort of came up with one of the first models in the 80s. So one has, mathematicians have all sorts of conjectures. So they have all kinds of beliefs of what makes a model behave in the same way as another model. Right? So we have lots of belief. Well, in particular, we believe that this Tetris model is in this KPZ universality class, and every model of interface growth with a couple of conditions should be in this universality class. Right? But the problem at the moment is that we don't. So first, we have a description of this conjecturally universal object that you see in the limit at large scales. There is a somewhat explicit description, but it's a very complicated description. Right? So the Brownian motion has a rather simple description in terms of that heat equation, which was not such a complicated equation. Here, the description is horrendously complicated. So one doesn't have a simple description, and also one doesn't have any kind of theorem that tells us, well, here is a nice large class of models that actually all converge to the same object. So right now, the status is there is one very specific model that has very specific properties which we don't believe are important, but that are useful in order to prove things, and for that one, we can prove that it converges to its object. And then there's maybe one or two other models. So it's still a very sort of unsatisfactory situation from the mathematical point of view. So it's getting towards the end of time, so let me just skip a little bit. So the part of the story here where I got involved, if you want, is in trying to understand situations that are close to situations that we already understood before. So in this particular case, the situations that we already understood before are the ones where instead of having one region that kind of invades the other one, you have an interface between two regions, but the two regions are symmetric. Right? So the interface can move up and it can move down, and it has as much probability of moving up, it's as likely to move up as it is to move down. It doesn't see the difference between the two sides. And in that particular case, one has a good description of what happens at very large scales, and there's a simple description. It's very similar to this Brownian motion that we saw before. It's sort of like a space-time version of Brownian motion in some sense. And so then the idea was to say, well, now what happens if you take a model where it's almost symmetric, but not quite. So one of the sides of the interface is just a tiny bit more stable than the other one. So the interface is still allowed to move both up and down, but it's just that it wants to move up a little bit more than it wants to move down, but just a tiny bit. And so then, of course, since it's just a tiny bit more likely to move up than to move down, if you look at what happens at somehow reasonably large scales, it doesn't really see that discrepancy. And so you expect to basically see the same as in the symmetric case, which you understand very well. But then if you look at what happens at larger and larger scales, at some point you start to see the effect of discrepancy. And so then you can ask yourself what happens there. And so you can conjecture things. So people wrote down an equation, so it's this Parisi-Jang equation. And that equation was supposed to describe what happens in that intermediate, what people call a crossover regime. But now the problem with that equation is the following. So here's a simulation of this. Okay, so this is, right, so it's a little bit like, you see what I mean when I said it's a bit like a space-time version of Brownian motion. Right? If I freeze that moving, it really looks like a Brownian motion. Right? And actually that's a theorem, so we can really prove that these things look like a Brownian motion but in space. But now it sort of wobbles around. And now, one thing that you see in particular is that it's extremely rough. Right? So if you freeze it, it looks like it's gone in motion, which really looked everywhere like this square root function. Remember the other meeting. And so at every point, this thing kind of looks a bit like a square root function, so it doesn't really have a slope anywhere. Right? So it sort of wiggles around very, very fast because somehow infinite slope everywhere. But the equation that's supposed to describe it has this term here, which is the square of the slope. Right? And so that's kind of a problem. Because the thing that you would think is a solution doesn't have a slope anywhere, but the equation that describes it involves the square of the slope. And so they say, well, so the equation is nonsensical, so it's kind of the wrong equation or something like this. But turns out that actually it is somehow the right equation. So there's what you would want to do is you want to say, well, the slope is sort of infinite, so the square of the slope is infinite, obviously. So you have to sort of subtract the right infinity and kind of make it finite, which sounds kind of like nonsense. But what does it actually mean? So here, subtracting a large number. So what it really means is that this equation is really some sort of idealized equation that you get in the limit. So it's really a limit of things that do have finite slope. It's just that the slope gets bigger and bigger, right? And it's only in this idealized limit that it's infinite. And so when you're not quite at the limit, the slope is just very big, then what it means that, well, you actually have to subtract a very big number. And the interpretation here is really, so for people who are a little bit familiar with these kind of equations, subtracting a big number on the right-hand side in some sense doesn't really do anything to the solution. All it does is it changes the reference frame. So what it really says is that this interface sort of wants to move up very fast. And so if you just look at what happens here, then you instantly don't see it anymore because it's moved up too fast. And so what you have to do is you have to kind of move up with it in order to keep it kind of centered. And so you can kind of interpret that infinity as really just some kind of recentering. So it really doesn't actually change the equation, it just centers it. Right? But obviously mathematically it's a bit tricky. And so you can come up with a theory. And so it's kind of the area that I've been working on in the last few years. So that's coming up with theories to deal with this kind of problem. Right? But I think we'll probably stop here for today. And thank you very much for your attention.